2017.
Hello, everybody. So, like you said, this talk is entitled Transforming Open Source to Open Access and Closed Applications. Specifically, we're going to be talking today about how, when auditing open source components of applications like Adobe Reader, you can find bugs easier instead of looking at the binary and transfer those bugs into the closed source applications, which then you can actually leverage to write exploits. We're going to go over several code matching techniques that exist, and we'll also go through a series of case studies that will show the underlying vulnerability in the open source component, how to pinpoint it in the DLL that's shipped with Reader, along with how Adobe actually patched the vulnerability itself. So first, the quick introductions. If you don't know who I am, my name is Brian Gorenc. I'm Malicious Input on Twitter, though I'm never really on Twitter. I'm the senior manager for vulnerability research inside of Trend Micro's Tipping Point organization. My primary purpose in my life basically now is to run the Zero-Day Initiative program, which represents the world's largest vendor-agnostic bug bounty program. Now, what does that mean? That means we work with researchers around the world. We purchase zero-day vulnerabilities from researchers, a lot here in the EU and in this region. We produce detection guidance for the Tipping Point IPS, and then we ship them to the vendors to get them fixed. We do a lot of vulnerability purchasing and research inside of Microsoft and Adobe products, and in fact, we're actually one of the top suppliers for both of those vendors for vulnerabilities for multiple years now. I'm also responsible for organizing and adjudicating the ever-popular Pwn2Own hacking competition, which is actually happening in March at CanSec West. So if you have some zero days and some exploits that you would like to sell in a public forum, definitely come on out and check it out. I'll let my colleagues here introduce themselves.
So my name is Abdul. I'm a security researcher working for the Zero-Day Initiative program, which is part of Trend Micro now. I've been working for the ZDI for the past 4 years. I do a lot of vulnerability research, root cause analysis, and stuff like that. I'm based off Montreal, Canada.
All right, I'm Jasiel Spelman. I go by Wandering Glitch. I've been with ZDI since 2012, but I've been with Tipping Point for 11 and a half years now. I focus a lot on static analysis and reverse engineering and just really root cause analysis in general. That's about it.
All right. So, lucky for me, when we were going through this presentation, I drew the straw to talk about the attack surface that we're going to be going over, which means I get the lucky honor of presenting XSLT to this audience, which is very exciting for me because you likely already know all about XSLT. But there is a point to this section so that you can actually start, so we can put you in the right place in the Sablotron code to find vulnerabilities. So first, as we all know, it's very common now for applications to integrate open source projects into their closed source applications. It's a way for the vendors to quickly add features to the product without having to go through all of that really costly engineering effort. But one of the real problems that we're starting to see inside of the Zero-Day Initiative program is the vendors don't actually understand the security side effects that exist by integrating these products. There's a lot of misunderstood assumptions about how the code works, and as a result, this can interject security weaknesses into the applications that they're shipping to their end users. There's also a lot of poorly implemented components out there, or code that's no longer being maintained, and as a result, now the vendor has to take on that burden of keeping that open source project active and implementing security features into that project long after the project has died. There's also sometimes missing security mitigations that don't get rolled in. You know, some of the new mitigations that are being released in say Edge and things like that. You know, those types of ideas aren't actually implemented in some of this older code that's being integrated into the products. So what we're going to do is we're going to look at Adobe Reader. As we all know, Adobe Reader is a widely used document reader. It's got a ton of features for document authors to generate really complex documents. And in ZDI, we spent a lot of time looking at Adobe Reader. We've done several presentations over the last 2 years related to vulnerabilities in this product, including things related to JavaScript APIs, buffer overflows, use after freeze, all sorts of stuff that we've talked about. But what we're going to look at specifically today is the code that Adobe really didn't implement, the stuff that they're actually bringing in from the open source community and the vulnerabilities that exist in that. So We're going to highlight some of the security side effects that we just talked about in the previous slide. But if we look at Adobe Reader, it has several open source projects that it actually integrates, one being a modified version of libtiff for TIFF parsing, and also a modified version of Sablotron, which is used for extensible style sheet language transformation handling. And unfortunately for Adobe, the Sablotron project is now abandoned. There's no more community out there actually implementing new features. There's no security fixes going on in that project in the open source space. And so it's kind of left up to Adobe now to actually integrate and fix all the bugs that are coming into their Security Act group in this old code. Now, if you don't believe us, if that Sablotron is actually being used in Reader, well, you can actually leave the licensing information in the product. They show the fact that they are integrating that product, and it actually exists in AXSLE.dll. And we pulled the version information from the code, and you can see it on the screen here. It's actually using version 1.0.2 of Sablotron. And so this kind of just proof that it is actually integrated into that DLL. Now, XSLT has been around since the late 90s, was part of W3C's extensible style sheet language specifications, and it's used a lot by application developers to transform data into other formats, XML data into other formats. And back when I was developing code in my everyday life, I used XSLT a lot and XML a lot to define data and bring it into a system and transform it to different formats like HTML, plain text, or you can also transform it into XSL formatting objects for later use. But what's important about XSLT are the logic elements that exist that do processing. And these logic elements are used to describe the transformations that are going to be applied to the XML that it's transforming. So we have things like for each, which will select every XML node inside of a node set and perform processing on it. There's XSL attribute, which will create an attribute on a node, an output node. There's copy that will copy node and put it to the output. And there's value of, which will actually select the value of the XML node and print it out into the output. Now, to also understand the XSLT format, you also need to understand how XPath works, because XPath is used to query the XML document to select nodes and perform calculations on the data that's coming in as it's going to be transformed. You know, I put a XSLT or an XPath on the screen here, /music/artist, square bracket 1. This is going to select the first artist element that is a child of a music element in an XML document and then allow it to have processing performed on it. Now, XPath functions actually add flexibility to the XPath itself. You can use node set to actually get a set of nodes related to XML, string to actually do evaluations on different string arguments, Boolean and number to do the same thing for Booleans and numbers. So there's a lot of functionality that exists in XPath and a lot of code that exists in these projects that can be audited and looked at for vulnerabilities. So XSLT transform, really simple, looks like this on the screen. It's probably hard to read in the back, but this XML on your left is a XML that contains a catalog with multiple CDs, which a bunch of metadata related to the CD itself. And then in the middle here, there's actually an XSLT document that's going to transform that XML into the HTML that you see on the screen. And you can look at if you look at the XML, it's kind of hard to see, but there is a for each logic element in here that's going to select every CD that is a child of catalog and then perform processing on it using the value of XSLT logic element. So as a result, you can start doing processing and transforming data that is XML formatted into HTML and produce this really amazing CD collection HTML page, which everybody loves. So if we look at exactly how you would actually call the underlying XSLT engine in Adobe Reader, you have many ways in Adobe Reader to actually do that. One is XFA, and the more common way that we're seeing is actually people using JavaScript APIs to trigger that underlying engine. So what we see here is in the first variable is actually the XML document that we're going to transform. The next variable is the XSL document, the transform itself. This will trigger the underlying code that we can use to trigger vulnerabilities in the XSLT engine. What you have to do is you have to parse the XML document variable, bring it into a DOM, and then select the root node, and then apply the XSL transform on that root node. And underneath the covers, you're going to be exercising the Sablotron source code that has been compiled into AXSLE.dll. Now, this is just the beginning of how you start triggering some vulnerabilities in this code. To understand what type of bugs and where to look in the code, we're going to show you a couple places where you can at least start looking for bugs. In this case, what you're seeing is the definition of all the different logic elements that exist in Sablotron that's being used by Adobe Reader. And this enumeration here talks about the different, defines the different logic elements, and you can see that copy of is in there, value of is in there, attribute is in there, for each. All of the different XSLT logic elements are defined here. Now, where is the processing for all of these different logic elements located? Well, there's a class in Sablotron called XSLElement, and inside the execute method, there's actually a giant switch case that actually goes through and performs processing on the different logic elements. So if you're going to go start looking for vulnerabilities as it relates to the processing of XSL logic elements, you want to start looking in the execute method. And we'll actually talk about in Abdul's section about some vulnerabilities that existed in this code. Now, XPath functions are also implemented in Sablotron, and these reside in expr.cpp. And again, it's another switch statement that exists in this code, an expression call func method. And we've listed some here on the slides, but there has been vulnerabilities in XPath processing as well. And so you can actually, if you're going to go audit and look for vulnerabilities in this open source code, you want to look here for XPath style vulnerabilities, and then you can transform those into the same vulnerabilities inside of Adobe Reader. Now, we've also seen inside of this code some issues related to heap and list implementations, and so it's another place for you to start looking. If we look back at the vulnerabilities that have occurred inside of Adobe Reader's XSLT engine, we can see back in 2002, Adobe actually fixed 2 vulnerabilities in this engine, and we'll talk about those bugs here in a second. They've got an interesting backstory that actually affects the latest patch that Abdul will talk about. These were discussed at length on the conference circuit, but the community really hasn't paid attention to this code base much since those discussions. Then in the Zero Day Initiative program in 2015, we started to see new submissions from multiple researchers in this code base coming into our program, and it got us interested in how exactly they were going about finding the vulnerabilities in Adobe Reader, and it all comes back to source code analysis of Sablotron and fuzzing techniques that they're using to finding these bugs. And so we'll kind of go over some of those here in a second. Now, to kind of give you an idea of where some of the bugs are located, we generated this table here. The name column just has the different source code locations for code inside of Sablotron, along with descriptions of what that code actually does, and then the corresponding CVEs that were discovered in those source code locations. And you can see there's a couple here from 2012, and the rest of them are from 2016. In fact, all of these bugs were actually, I believe, patched in January of this year, but assigned CVEs of 2016 for whatever reason. So what we're going to do now is I'm going to hand it over to Jasiel, where he's going to talk about how you can pinpoint the vulnerability in a closed source application using some techniques after you've audited the code of Sablotron to find bugs.
So the first thing I want to mention is that we're not doing a straight bin diff against a built binary, in part because initially wasn't entirely sure how easy it'd be to build it, but also because there are a number of preprocessor defines, and you can't, initially we didn't know whether or not what all those values were. In addition to that, Adobe has implemented a decent number of changes on top of what's public. They did open source their modifications a few years ago, but they have not done so anytime in the recent past. And the Sablotron source that is available is incredibly old. So start off using something that is a very, very well-known technique, and that's just looking for strings. So here we have this struct has a pointer to a string, followed by two enum values, an xfunctor and xtype. But in the binary, that's just going to look like raw integers. And since this is a 32-bit application that we're looking at, it's only going to be a D word each. And so if we look for last in position, we see a structure, and we can kind of glean that this is the exact same structure we were just looking at, the func information table. On its own, this structure is not all that useful, specifically because it does map from the XSLT function names to their IDs, but then their IDs are not the easiest to find. And if you were to do a search for, say, last, which is hex 1A, you'll get a bunch of references or a bunch of hits and not really go anywhere. Thankfully, one of the entries in there is one that's called system property, and that one has a value, it has an ID of hex 3B and takes a string. And this one is specifically useful because if you look at the code, it is responsible for returning version information of the XSLT engine itself. Looking at the code, we see that within this call function, we have a switch statement, which I kind of hid away, but in this particular case, for system property, we have a few strings that are guaranteed to be referenced. And this is just quite fantastic. For whatever reason, Adobe never modified this, and this code base is so old that gingerall.com is now, I think, a Polish website for some other completely different purpose, not software related at all. But by looking for these strings and then looking for where one particular function in particular uses them, we're able to see exactly where call func may be. And it ends up being this function, which is probably impossible to read. It's perfectly fine, though. But it references vendor, vendor URI, Ginger Alliance, and gingerall.com. And if we were to keep going up, we would eventually see that EXFF system property value being referenced. I would have shown that, but it ends up being kind of worthless in that math is performed on it, and it doesn't end up being hex 3B like it is in the structure itself. Kind of expanding on that, and one that is incredibly useful, I've used it in Reader a lot and in Flash, is looking for just data structures. So in the previous example, we had a pointer to a string followed by two integers, and those integers were just enum values. But you can expand on that and look for any array or any const structure where you have a bunch of static data. This also works for if a function has static data and is going to place it in the data section, because then you can look for those values, and more often than not, you're able to find them. Sometimes a compiler will create multiple copies of a table, but you can still find the references and then do kind of basic code matching techniques on top of that. So in this particular case, EX token is an enum, and token @ token d:, token l paren, and l bracket were all I looked for. Basically just converting those into little Indian D words and then looking for the raw hex string, and ended up finding exactly that string, so hex B, hex D, 5 and 7, and now we know exactly where the namer table is. Using this, was able to then find where some of the UTF-8 functions that Abdul will be talking about were located. Kind of in the same vein, you can just do looking for straight hex values. For one of the functions that was vulnerable, Abdul just looked for hex DC00 or hex CD00, one of the two, and was able to find and isolate the function. But being able to look for data structures themselves can be incredibly useful. One of the things I had mentioned about not being able to build and do a bin diff against that is that you have preprocessor defines. And this is probably also not very readable, but you have huge chunks of code in Sablotron that are going to vary based on the value of these preprocessor values. And in this particular case, you have basically an entire function that will look very, very different based on that. There aren't that many places where you can kind of discern what that looks like outside of looking at a particular function and looking for the absence of or presence of certain code blocks. But thankfully, there are a few places, such as this XSL op name structure, that has a string that is only present when this CT_change, which is one of the more prevalent preprocessor defines, is actually defined. So by looking for forward compatible, we're able to see that that in the production builds of Adobe Reader, they did in fact use CT_change. And on that note, I'm going to hand it over to Abdul so we can go over bugs themselves.
All right. So I'm going to be covering a bunch of bugs here, basically the previous ones that have been found in the XSLT parser in Adobe Reader. I'm going to go over a bunch of bugs of different types. I'll also be covering 2 old bugs, the first 2 bugs that were found by Nicolas Grégoire, also known as goes by Agari. One is a heap-based buffer overflow, and the other one is a type confusion. The reason for us going through these bugs is that it gives us an idea of how Adobe patches these bugs. Basically, they patch these bugs twice, once in 2012 and once in 2016. So basically, there was like a 4 years gap between these 2 patches. So it's kind of interesting. So I'll start off with the heap-based buffer overflow. So XSL elements in Sablotron are parsed inside a class called XSLElement. And inside it has a method called execute that contains a big switch case and parses the elements based on the type. So the way this works is that it checks whether each element has a name attribute, and then what it does is it grabs the value, and then calculates the length of it, allocates like a buffer based on that length, and then tries to convert it from UTF-8 to UTF-16. And this is done inside a function called isValid and CName. Basically, as you guys can see, I don't think you guys can see in the back, but it does the string calculation inside UTF-8 str length, and then it allocates a buffer, passes it to UTF-8 to UTF-16 for the conversion. So we went back to Sablotron source code just to do some analysis, and we figured out that the core of this bug was because of the way the string, the length of the string was being calculated, basically inside UTF-8 str length. And the way this works is that it loops through the string, like byte by byte, and checks for the length of it, of each byte, of each character basically, and it keeps incrementing by 1. But in special cases, when you have like a Unicode string or something like that, it doesn't calculate it. It actually calculates it, but it doesn't add the length to the count. But it keeps incrementing the count by 1. So that basically leads to a miscalculated length. That length is later used in an allocation, and then it's passed to UTF-8 to UTF-16, where the actual heap-based buffer overflow happens. All right, so the way we pointed this out in Adobe, basically in the DLL, the compiled DLL, is by looking for DC00. And if you do that, then it's directly going to land you inside UTF-8 to UTF-16. So the decompiled code here basically roughly matches the Sablotron source code. So Adobe didn't really touch that code. They didn't modify anything. And from UTF-8 to UTF-16, you just can grab the extrafs, and then you're going to end up in isValid and CName. The first function called inside and CName basically is the UTF-8 str length. And this is the same case, it hasn't been touched, so it's roughly the same code in Sablotron, which is kind of interesting. All right, so as of the patch, the way they patched it back in 2012 was kind of interesting. So we grabbed a bunch of DLLs from previous versions, and Adobe is generous enough to put all these, the previous binaries on their FTP server. And we were kind of expecting to see some changes inside the length calculation function. But in fact, what they did is they modified the conversion function, and they added an extra argument to it, which is the source length. And then obviously they just use it to keep track of what's being written, which didn't actually make sense. So until 2016, when we received like a bug from the same researcher, Nicolas Grégoire, he submitted the bug that retriggered the same exact crash. So we submitted this bug to Adobe, and then it got patched in January 2017, like a couple of weeks ago. We diffed the bug, and this time they actually did it right. So they modified the UTF-8 single car length. excuse me, they actually modified the UTF still length function that does the calculation. And in this specific case, you guys can see that it calls UTF-8 single car length just to calculate the actual character length, and then they add it to the count instead of just incrementing the count by 1. So basically, they got it right like 4 years later. All right, so the next bug that I'm going to be discussing is the second bug that was discovered by Nicholas back in 2012. And basically, this is a type confusion bug. He specifically describes it as a sexy type confusion, which is kind of cool. All right, so the root cause of this bug is in an XPath function called lang. So the way lang works, basically, it just, first of all, it checks the number of arguments that's being passed to it. It checks whether, it checks the type of the argument. In case that lang is being executed against the node set, what it does is it tries to convert nodes to elements, and that's being done inside a macro called 2e. So 2e is specifically interesting as it uses another macro called cast. And cast is an interesting case as basically it calls dynamic cast, but it does it in the debug mode. In production, it just does it this like the classic C style, and that's basically what causes the whole type confusion issue. So pointing this out in Adobe is pretty much straightforward. All we have to do is just like run a search on lang, and then we're going to end up with 3 hits, and it's pretty much trivial to find the right one. So the right one is going to land you inside a function with a huge switch case. This is not a problem. Pretty much easy. So it's the same case that happened with the previous one. Basically, Nicholas submitted a POC in 2016 that triggered this bug again. And again, we went back with the old DLLs and we started diffing just to see what happened back in 2012. And basically what they did is they just make sure that a certain type of node is being casted right, but you can re-trigger the bug again by giving it like other types of nodes, and that's exactly what Nicholas did. Basically, he gave it a comment node, I guess, and some other type of text node, and he was able to trigger it. This is the diff of the January 2017 patch, and basically they did it right this time, and they called a function called RT dynamic cast to do the casting in the right way. All right, so I'm going to be talking about some modern bugs. Basically, this one is an out-of-bound read. It's one of my favorite. It's really easy to spot in source code. It was found by one of our researchers called Wei Li. He's based off Singapore. All right. So this one is in the way XPath functions are being handled inside Sablotron. Basically, the way it works when like the XPath functions in Sablotron, they check for the arguments first, the argument types, and then it references these arguments. And all the checks are being done inside macros. So for example, check args count, basically it checks if the number of arguments is right. If not, then it's going to bail out, basically. So if you check this pattern inside a function called callfunc that implements all the XPath functions, you're gonna notice that what happens is they check args and they reference these args. Only in one case, which is a substring after and substring before, they reference the args and then they check for the args. And that's exactly what happened here, and this caused the out-of-bound read. All right. So it's not that easy to spot this one. Basically, this is just the function that contains the whole switch case that implements all these XPath functions. But you can use one of the techniques that I described before, which is basically just look for lang, and then you're gonna be able to just land inside callfunc, and from there you can calculate the case number, and then you can land in substring before and after. By the way, both are handled inside the same switch case, so it's all good. So as for the patch, I think you guys would probably figured it out. They just moved the args check before referencing the actual args, so it's kind of straightforward. All right, so the next one that I'm going to be talking about is a little bit more complicated than the other one. It's an out-of-bound write, and it has been found by Whaley too. So this one basically affects like how lists are being implemented inside Sablotron. So Sablotron implements the list objects, and they're just basic structure of ordered lists according to what they say. Anyways, so two things we have to notice, or we have to study about this list object, which is the constructor and the append method. So in the constructor, a variable called original block size is being set to 2 to the power log block size, and there's no check against that value whatsoever. In append specifically, that value is used in an allocation of a buffer, and then a value is being appended to that specific block. And the nice thing about it is that if someone controls that size, that length, then they can trigger some kind of integer wrap, eventually allocating a very small buffer and then writing out of bound to that buffer, to that object. So this is specifically what happened inside create context. Basically, all the XPath expressions are handled inside that create context function. So first, it defines a list variable called reached, and it's set to the predicates count. So basically, predicates are things that the user can control inside XPath expressions. So in this case, the preds count is controlled by the user, and later there's a call to reach that append 0. So basically, if a user defines a certain number of preds count, then he will be able to trigger like an integer wrap, which is then be passed, the value is going to be passed to an allocation, and then we'll be able to write out of bound. All right, so pinpointing this one is Adobe is not really straightforward. First, we have to find create context, and from there, we will be able to find create LP context level. That function calls a function twice. I called it list constructor. And if you decompile it, you're going to see exactly that it matches the Sablotron code, and nothing has been changed there too. So the next function that we can check, which is list append, basically Adobe just copied pasted the same thing. They didn't modify any of the code, and as you guys can see, it does the same thing. Grabs that original block size, use it in an allocation, and then writes to that block. All right, as for the patch, Adobe patched it in a really interesting way. Personally, I was expecting them to do some checks on the variable initially, but what they did is they implemented some checks inside the append function. So they made sure that the value is in a certain range. If not, then it's going to be set to a negative value, and then the allocation is going to fail. So basically, the check is check if the length is greater than 4000, or is a negative value. If that check succeeds, then fine. If it fails, then it's going to be set to -1, and then the allocation just fail. So the last bug that I'm going to be covering is a double free, and this one was found by Whaley too. Interestingly, Nicholas found this bug too. He submitted it to us, but we had to reject it because it was a duplicate submission. So inside Sablotron, they implement something called the guarded pointers, and basically these are pointers that they allocate themselves automatically on exit, or when something out of band happens, like an error is triggered, or anything like that. So what's interesting about the implementation is the assignment operator, which returns a row pointer. So you cannot actually track these, or there's no counter for these, or reference counting as we call it. So in certain cases, if you have a reference to a GP inside a function, there's no way that the function can guarantee the lifetime of these pointers. So basically, if an error is triggered, then the first pointer is going to be freed, and then the reference is going to be freed, and then you're going to end up in a bad situation. So this specifically happened inside the AXF filter case. Okay, this is really bad. So in the end, there's, right here, there's a filtered C GP pointer, which is assigned to new C, which is set to new C, and basically you're gonna end up with a row pointer inside filtered C. When you're dealing with XPath functions, you can force it to trigger an error by calling a fake function, and that's gonna force these GP pointers to deallocate or to free themselves. So you're gonna end up with new C being freed and then filtered C to be freed too. So you're gonna end up in a double free situation here. So Adobe implemented this in a really interesting way. Basically, as you guys can see, it just retrieves the reference and then stores it in another local variable. Later in code, it just grabs one reference and then deletes it, and then grabs the other variable and then deletes it too. And that's how the bug was triggered in Adobe. So as for the patch, they patched it in a really interesting way too, which is basically they removed the code responsible for deleting the second reference, but you still have a reference in the stack variable. So if someone actually was able to force that reference to deallocate again, then you're going to be in a difficult situation. So I'm going to give it to turn it to Brian now. So he can conclude all this, wrap it up.
All right. So why is all this interesting? The thing is instead of having to actually audit the binary, you can go directly to the source and look for vulnerabilities and find vulnerabilities in a lot easier way. So Sablotron has been around for a long time, and one of the things that we actually learned by looking at it is I think we looked back to Adobe Reader 9. Yeah. So Abdul did some analysis where he looked at the DLL that was containing the XSLT engine. He looked back every single release of Adobe Reader since Adobe Reader 9 came out, and they've really only implemented security fixes in every one of those updates. And in a white paper that we'll release in the coming months, we'll go over basically every single security fix that they've implemented inside of this engine over the years, and it really provides like an interesting way you can use some of the techniques that Jasiel talked about related to pinpointing the vulnerability in Adobe Reader and look for that vulnerability in the code. And for programs like the Zero Day Initiative where we're buying vulnerabilities, I mean, that's a perfectly valid way to go look for bugs and find bugs. And if you look at our contest, we actually would pay somebody like $50,000 for an exploit against Adobe Reader and they could easily just go audit some open source code, find the bugs in Adobe Reader, and write an exploit and bring it to the contest. So it's an interesting technique that you can use. Adobe Reader is a very, very popular software inside of enterprises. In fact, I was meeting with some government officials this morning, and I was looking at their laptops. All of them had Adobe Reader on it. So it makes a very, very interesting target to go audit and look at. Many of these projects, no longer have communities available to them to develop security fixes or any improvements at all, and it's really then on the vendor to go find and fix the incoming security vulnerabilities. And because they didn't implement the code to begin with, they may not have a good understanding. And as we've seen here with the bugs that Abdul has talked about, is that many times they don't actually fix them correctly. And so the two bugs that were actually discovered in 2012 had been around, still around for many, many years until they were patched most recently with the new incoming submissions into our program. So just kind of leave it at that. It's an interesting code base to look at. You can kind of transform those open source bugs into closed source application weaknesses, and we hope you enjoyed the presentation. We're here to answer any questions if you have any.
Yes, so I have a question regarding not automatically matching source to binary by compiling the source. So you said the defines become an issue because you don't know which defines are used by Adobe. Have you tried similarity techniques to find which defines are used or not? Like automatically trying to determine these?
So we have, but at least when I'm doing things, I like to go more I like to be very static and know for sure, and so finding things like that array of strings where you know for sure that it has that particular define, I usually try and go for that just so I know I can build a list rather than having to do bin diff similarities. That's just personal preference, though.
Perfect. Thank you very much.
Thank you.